Welcome to this presentation on solid edge simulation. I hope this presentation will be interesting, informative, thought-provoking, and allow you to think about your company's processes in a different way. You will discover the business benefits of incorporating FEA analysis early in the design process and ease of use of this feature-rich solid edge offering. Here is the agenda for today's presentation. We'll look at the trends and challenges that are facing design engineers today, how solid edge simulation helps meeting these challenges. We'll take a look at how Siemens is responding to the challenges with the capabilities that exist in today's solid edge simulation. I will take you through an overview of solid edge simulation capabilities, business value, and a case study. And finally, I hope to have some time at the end of today's session for you to ask any questions regarding what you have seen. Here is a research from Aberdeen's group called Cost-Saving Strategies for Engineering. It clearly showed that regardless of the economy state, profitability remains the top priority of many companies. They are looking for ways to deliver quality products while reducing costs. When armed with the right resources, engineers are empowered to make the better decisions, reduce the cost, and improve bottom line for the company. To understand the external factors driving companies to improve their design process, survey respondents were asked to pick the top two pressures driving those improvements. The top pressure is reducing product cost. It's currently the most important factor driving improvements in product design. Much of the final cost of a product is determined by the decisions engineering makes during the design phase. At number two is the need to get products to market as quickly as possible. This means engineers must find ways to take out costs of the product without adding a lot of additional time to overall development process. Balancing these mentioned pressures constitutes a considerable challenge. So Aberdeen's research indicates that making these trade-offs is a top product design challenge. Looking at this graph, you can conclude that it's difficult to predict how all the facets of the design will come together in the final product. In order to respond to these challenges, engineers need access to the tools that will provide them with ability to make the best decisions for the product. Simulation early in the design process gives them access to the required information. Best-in-class strategies simulate early, simulate often. Analysis of the best-in-class performance indicates a strategic emphasis on using simulation to gain better insight into the product behavior. Introducing this in the beginning of the design process is a key differentiator of success. The best-in-class are also likely to implement a get-it-right the first time strategy. This refers to use of simulation throughout the design process to correct product performance before any physical prototypes are built. So what are the issues facing design engineers today? The job that today's engineers are faced with has to cover a multitude of tasks in all phases of product development, including analysis, and involves the use of several products, each with its own user interface and method of working. Often, tasks like simulation are outsourced, which has the effect of separating analysis from the design process. This reduces the number of analyses that can be performed and prevents analysis from being used for investigative studies, which overall inhibits innovation in the design. Some of the solutions available today are overly simplistic, which can compromise solution accuracy and create misleading results. The inability to edit geometry easily after analysis and the lack of CAD associativity with simulation inhibit the fast turnaround necessary for timely and effective design refinements. Solid edge simulation is one single integrated environment. It's using the same underlying geometry and user interface as all solid edge applications. Solid edge simulation is easy enough for any solid edge user who has a fundamental understanding of FEA principles, yet robust enough to service most of your analysis needs. By enabling engineers to perform their own simulation, more analysis gets done in less time, improving quality, reducing material costs, and minimizing the need for physical prototypes without incurring the high cost of outsourced analysis. The layout of user interface is designed to guide the user through the whole analysis process, which makes it easy to learn initially and revisit if necessary. This slide shows you the depth and breadth of current SolidEdge portfolio. If you look at all the solutions highlighted in black, these were all launched in the last few years, so huge investment from Siemens into SolidEdge. Note that SolidEdge simulation goes into the third column, specifically dedicated to FEA products that are part of SolidEdge portfolio. Siemens recognizes the importance of delivering highly capable analysis tools to the customer base. SolidEdge portfolio covers majority of analysis needs encountered by customers. Besides mechanical simulation, there are tools for heat transfer analysis. Thermal simulation in the SolidEdge simulation is mainly thermal conduction, which is the heat transfer inside of the objects. This helps users to simulate the thermal effects to the structure, such as thermal stress. The heat convection depends on the fluid flow. It's important to simulate the fluid flow to understand the heat convection performance. The FloEFD is the fluid flow simulation solution, but it can handle the heat convection along with the fluid flow. SolidEdge simulation provides both automatic and manual methods of mesh creation with the precise local mesh control for higher accuracy. Full complement of loads and constraints is available for defining realistic operating environments. The underlying solver technology is an XNestron, de facto industry standard solver for finite element analysis. Variety of analysis can be performed including statics, normal modes, frequency response, buckling, and heat transfer. Users can interpret and understand the resulting model behavior quickly with the comprehensive graphical post-processing tools. Simcenter technology allows for history-free model changes at will, which drastically speeds up the model refinement process. SolidEdge simulation can take advantage of Simcenter FloEFD for SolidEdge, which is part of SolidEdge portfolio. FloEFD is a fully CAD-embedded computational fluid dynamics software that is used to perform analysis of heat transfer and fluid flow design. Key FloEFD features are an intuitive user interface, which means short learning curve, a use of native SolidEdge CAD data, no transition or fluid body creation needed, automatic recognition of model changes, so geometry and simulation data are synchronized, fast automated mesher, and unique solver that gets accurate results fast. Fluid pressure and temperature results can be imported from Simcenter FloEFD as structural loads for analysis. Integration between the two solutions is seamless and easy, as both are fully embedded in the SolidEdge environment. Simulation functionality scales from individual parts to analysis of large assemblies, all the way to FEMAP with Nestron, enabling engineers to define and analyze complete systems. FEMAP is widely used in aerospace, defense, marine industry, particularly for airframe loads, space vehicle stress and dynamics, and analysis of ship hull and offshore platforms. The starting point for FEA model creation is generally the CAD model. FEMAP can be launched directly from SolidEdge, transferring in the geometry for analysis. FEMAP has some extensive CAD model cleanup tools, in-depth functionality for mesh creation and editing, and can work well with orphan meshes for FEA model reuse. Complete geometry and finite element models with boundary conditions and results can be seamlessly transferred from SolidEdge to FEMAP by saving the simulation model as a FEMAP file. Advanced type of simulation, such as nonlinear analysis, for instance, becomes easily accessible without losing any work done in SolidEdge simulation. So let's take a look at SolidEdge simulation in action. We're going to take advantage of tools available in SolidEdge, such as simplified models, as well as additional portfolio products for more accurate results. We're going to start by looking at solid edge simulation in action. And first example, we're going to take a look at this plowing mechanism assembly that would be attached to a plowing, snow plowing machine. And the first question would be how this bracket or this arm connecting this mechanism to frame can withstand the loads introduced by Mother Nature. So let's open this assembly and let's focus on this particular mechanism. First of all, I'd like to mention that solid edge simulation is tightly integrated with solid edge, and I'll prove this to you just in a second. But first, let's isolate information on the screen that we're going to be working with. And one thing I'd like to point out, one of the benefits, not the single one, but one of the benefits of this tightest integration is ability to use solid edge functionality that would help us in setting up study and getting results quickly and efficiently. First thing I'd like to point out that we can take advantage of ability to simplify the parts. This will reduce processing time and allow customers to get to the results much quicker. We can delete single rounds, or we can delete the whole feature. And in this case, I just got rid of all the features in this part. And when I say delete, I didn't mean delete completely. I meant that we can take this part and use simplified version of this part for our study. So let's start our simulation. It can be accessed directly from a simulation toolbar. And you can see I can create new study. Here we provide ability to analyze designs in many different ways. First of all, we provide ability to do linear static analysis, normal modes, linear buckling, steady state heat transfer, a combination of linear static and buckling with heat transfer analysis, harmonic response, which is essentially vibration analysis. And also we provide ability to define different type of mesh, which is very beneficial because sometimes you deal with a thin wall component that requires surface type of mesh, or even mixed type of mesh when you combine regular models with a thin wall components. So right now we're looking at linear static with tetrahedral mesh. We can select all the components and include them in our study. One thing I'd like to mention, that solid edge interface is very flexible, user-friendly. I can turn on the simulation as a sidebar and move logically from top to the bottom and apply loads, constraints, or I can go in simulation tab on the command bar and move from left to right. So let's start applying some loads. Before I do that, I can go quickly to original assembly and measure angle. This allows us to more precisely, let's say if I measure angle between the two faces, it gives us about 34 degrees. This will allow me to apply loads in more realistic way, mimicking real life condition. So let's go and apply loads. And again, we have many different type of loads depending on type of analysis. As you can see, right now we're doing linear analysis, so thermal loads are disabled. So we're going to start with the force, and we're going to apply force to this particular pin. One thing I'd like to mention, that the same type of tool we're using to manipulate geometry, which is steering wheel, we're using the same tool for applying, or I should say directing the force in this particular case. Conveniently, I can type in the value as a formula, as you can see, and system will allow me to position it properly. Also, I'd like to point out that solid edge simulation and solid edge is units neutral solution. So we can type in, let's say, 5,000 pounds of force, and the system will recalculate that and apply the load appropriately in those units that right now is active. As far as constraints, we have many different type of constraints. In this case, we're going to log these two pins that we can run analysis against. And finally, we came to a point where we need to define relationships between all these components. We can conveniently define automatic relationships. So we can select all the components, and with one single button click, system will present us with a list of different connectors that we can use in this particular case. If you want, you can get rid of some connectors or multiple, delete. In this case, I'm going to accept all the defaults. And in one single click, again, if I go to mesh dialog box, in one single click, I can mesh and solve immediately within the solid edge simulation environment. So this assembly is not very complex, so we can easily use mesh and solve in one single operation. As far as constraints, we have many different type of constraints. In this case, we're going to log these two pins that we can run analysis against. And finally, we came to a point where we need to define relationships between all these components. We can conveniently define automatic relationships. So we can select all the components, and with one single button click, system will present us with a list of different connectors that we can use in this particular case. If you want, you can get rid of some connectors or multiple, delete. In this case, I'm going to accept all the defaults. And in one single click, again, if I go to mesh dialog box, in one single click, I can mesh and solve immediately within the solid edge simulation environment. So this assembly is not very complex, so we can easily use mesh and solve in one single operation. Results pop in. We're looking at post-processing window, which is really important for interrogating results, and it provides users with many different options. We can take a look at animation. It's a very important part of the interrogation because you need to evaluate how the system performs under stress and make any adjustments if necessary. You can turn on, turn off different options. You can save it as AVI or movie. In this particular case, you can take a look at results in many different ways. In one in particular is ISO contour, where you can dynamically walk through your design and isolate specific value for your stress and take a look at how it distributes throughout the part. In this particular case, I'm interested in not only stress but factor of safety because it's a very important component. So users can define different custom values. Let's say we're looking at value between 4 and 5 since it's a very important component, and you can see this is not strong enough to support that factor of safety. So we can quickly go and customize our part. Again, conveniently, because it's one single integrated environment, I can immediately get access to the features of that part even from assembly level. I don't have to dive into part. I can pick this value and modify, make those ears slightly thicker. Also, maybe we don't need to have this so deep pocket here. Again, I can, using synchronous technology, I can easily manipulate this geometry on assembly level without diving inside of the component. And you can see how quickly I can manipulate with this face on the ear on the bottom. So let's say I want to make it slightly stronger, and of course I can beef up the whole part if I want to. So let's make it thicker by 10 millimeters. So you could see how quickly and efficiently I can modify the geometry, and they're pretty much done in no time without need to go into actual part. And because it's one single integrated environment, again, not only are we using the same tools to manipulate geometry, but all I have to do is just click solve. System knows how to remesh the model based on new configuration, geometry configuration. It knows how to apply all those boundary conditions, loads, and we're going to get results in no time. As you can see, stress is significantly less than previously, so we can easily go and switch to factor of safety and then define the same value that we're looking for before. And as you can see right now, the part is green throughout, which tells us that it's strong enough to withstand that particular load. And finally, if I go back and define, let's say, one meter stresses or displacement, I can easily capture this in a report. With one button click, I can capture report on my design and save it for future references or for design review. It gives us really nice table of contents. We can take a look at constraints, connectors, mesh information, results. We can easily identify results, and it's really a very convenient way of capturing results for, as I said, future reference or design reviews. So now that we understand how Solid Edge simulation works together with Solid Edge, how it's tightly integrated, let's take a look at more advanced usage cases for this type of functionality. So in the next step, I'm going to show you a really advanced type of load that we can handle with thermal analysis. So I have two studies created in this particular case, and we're going to be analyzing this brake mechanism. We're going to take a look at how we can control applying particular load via function versus just applying the steady state load. So first of all, I'm going to show you that we can go and create new function, and this particular function, let's call it, we'll give it name. In this particular case, we're interested in a real life simulation. Let's see if a driver apply brakes to the full extent. Let's say at the first position, the factor is 1, and we continue at the next interval, it's still 1. You can see how on the right hand side, factor versus time, we can see that the system gives us chance to actually simulate this function in a visual way. So for instance, at 200 units, we apply 0, which means that, let's say, driver released the brakes, but then he reapplied them again. And in this case, he reapplied them at half of the previous force. So we continue with this one, and then finally he released brakes again. So let's say at 500 units, we're back to 0. So you can see how we can quickly identify that time versus a factor versus time type of application of this constraint. We can save this function. And in this case, if we go back to loads, we can easily identify a particular load, which is heat flux, and we can define, instead of applying steady state load, we can apply this particular function and solve it. I'm not going to waste your time solving it. We're going to just take a look at the results. And we applied the similar function in the second study. One of the convenient and very efficient ways of looking at these results is to probe the results. We can easily identify different points and probe different results, so we can easily identify values for the temperature, and we can quickly display the graph that shows actually distribution of temperature versus time. So in this case, we're looking at transient type of analysis, which means that temperature is changing versus time. At first, when driver applied brakes the full force, we're up to 200 degrees, then it's released, and then again it applied the half force. So we can save this graph with the file, and again it's available later for reviews or future analysis. So you could see how in this particular case it's very beneficial to have this new ability to apply function when it comes to different loads, when we talk about transient type of analysis. Now let's take a look at how different products within Solid Edge portfolio under Solid Edge umbrella will help users efficiently analyze their designs and arrive at the most optimum solutions. In this particular case, we're going to use Motion, which is now part of Solid Edge portfolio products and includes full dynamic designer functionality. We're going to bring loads from that environment and apply in Solid Edge simulation. In order for this to happen, all we have to do just create a single study. And in this particular case, we're interested in the crankshaft. And as far as constraints, all we have to do just fix these two faces outside of the crankshaft, and we're pretty much done. That's all that is required. We're not going to apply loads manually because, as I mentioned, under environments tab, we'll find motion environment. And once system takes us into motion environment, we can easily create new study and new mechanism, I should say, cylinder analysis. And you can see that there is a tight integration between these products because we're using the same environment pretty much. It's inside of Solid Edge, and based on Solid Edge relationships, Solid Edge assembly relationships, components are placed automatically in the categories of moving components and grounded parts. And you can see system conveniently placed them appropriately in correct categories. So, but you notice that joints are not created, and joints are the ones responsible for definition of movements inside of this analysis tool. So we can, of course, go and create those joints manually. We can define the orientation, we can define position, and create those joints as we go along. And you can see we have all kind of different joints available: cylindrical, spherical, revolute, translation, and so on. But let me show you the benefits that user derive from using this one single integrated environment. So once I go back to Solid Edge environment and go into Assembly Relationship Manager, we can see that a lot of these relationships are suppressed. So very conveniently, we can select all of them and unsuppress all at once. And now when we go back to motion environment, you can see that system immediately picks up on the fact that we have now new relationships. So at this point, you can see that all the joints required for this mechanism to act properly are created automatically. This is great time saver and effort saver. So for users, this help is invaluable. Let's move on and let's define some forces. But before I do that, I want to go in system default and show you how flexible the system is. So right now, by default, solid edge motion didn't know about in which direction we want gravity to act on it. So we change direction for gravity. While we're here, we can easily change the parameters of our animation. And you can see if I start our simulation, you can see that under the simulation system, under gravity, the system moves in a proper way. But it moves not in a consistent way because only gravity is affecting right now this mechanism. So let's go and apply additional joint. First of all, we can select one of the joints and go into properties and switch from free type of motion to velocity, 360 degrees per second. And once we apply that, we can see that now motion performs the way it's supposed to happen. And another thing I'd like to point out that the whole reason we're doing this, we want to extract forces that acting on this crankshaft. And that can be easily accomplished. Now, within motion, within solid edge, we can apply forces. For instance, we can apply force that act as a pushing force on this piston. So we can define position, we can define orientation. We have ability to switch direction of this force acting on the piston, and at the same time we can conveniently define the value. Based on some research I've done, it's about 1150 newtons for single cylinder of average car that acting on that piston. We need also to transfer that force acting on a piston into this couple, the conrod and the crankshaft. That can be easily accomplished via properties. So we can go in FEA and define how those FEA parameters would apply. The system even conveniently gives us a hand, so we can see that first component is a conrod. So we can turn off crankshaft and select the cylindrical face on the conrod, and then select the corresponding face on crankshaft. And now, since we created this, we can easily animate, or I should say simulate, our design. And the advantage of applying dynamic forces is that we can always go back to, let's say, this revolute and plot different characteristics. So we can plot reaction force acting on that couple. So we can plot X component reaction force, and we're going to plot Y component. We have many different options when it comes to plotting. We can plot momentum, we can plot different other characteristics. Not only we can see where the force is the greatest, and you can see the greatest it's in the Y direction, but by clicking at this diagram, we can place the mechanism in appropriate position where the force is the greatest. And once we've done that, we can easily right-click on that crankshaft node and say add loads. And solid edge constantly looking over your shoulder to make sure that you're not missing anything. So in this particular case, it's missing some FAA definition for crankshaft, so we can add those couple faces, and we pretty much transfer the load in the most critical orientation to the simulation environment. So when we exit motion, and you can see that all kind of forces, torque, and gravity applied appropriately based on that simulation inside a motion environment. You can imagine that it would be very hard to come up with this type of loads on your own without help of motion. And what's left to do is pretty much just mesh and solve. And this is really simple case, so meshing and solving will take only a couple seconds. And when we look at the results, of course, inside of solid edge environment, we can easily animate this, and we can see how this mechanism is deformed under the loads derived from motion. In the next segment, we're going to take advantage of ability to import pressure from FA analysis. In this particular case, we're looking at pipe reducer. You can see that flow of a liquid go through a bigger diameter pipe into smaller diameter, and they're connected with reducer. So let's see how we can easily import that information into our solid edge simulation. So in this case, I'm looking at the results in load results into flow analysis, which is again available as a part of solid edge portfolio products. And let me show the plot for cut plots as well as flow trajectory. And if we hide all the components, we can easily animate these particular results. And as you can see, as we're looking at this particular case, we can see that pressure drops from a bigger diameter to smaller diameter, while velocity is increasing based on a color map to this animation. Let's stop this animation. And now we're ready to actually export these results into solid edge simulation study. All we have to do is just go under Tools and Export Results to Simulation. So now we're ready to go to solid edge simulation, and actually under Loads, we can conveniently import these flow pressure results and apply to our study. And all we have to do is just solve it. So you can see how easily we can take advantage of master model approach. In this particular case, everything that model in solid edge, we were able to take advantage, figuring out the pressure inside of this structure, and then bring results back as loads in solid edge simulation and solve the study against that load. So let's talk about solid edge simulation packaging. Powerful, scalable solution offerings allow companies to select the best simulation tools for their specific requirements. Whether it's linear static, vibration, or heat transfer types of analysis, companies can save money by choosing the appropriate configuration of their simulation tools. So let's talk about some use cases out there. John Harder Company is an example of a great success in using solid edge simulation for streamlining their processes. As a result, design time cut from 4 hours to 15 minutes, job quotes drop from hours to 20 minutes, and they were able to meet OEM weight certifications. Another company that benefited from solid edge simulation was Codler. It belongs to industrial machinery and heavy equipment, the manufacturer of high-quality pumping solutions. Size and weight optimization, design integrity, materials waste avoided are just a few benefits to name. Let's summarize the benefits that our customers are getting from solid edge simulation. They're getting their products to market quicker by doing the design faster. They're making more innovative and competitive products by improving their designs, and they're reducing costs by doing more virtual prototyping. This brings us to the end of our today's presentation. Thank you for your time today. Now we're going to open for any questions you might have.